Hello everyone, my name is Aghabalapoor. I'm master's student in physical engineering at Istanbul Technical University of Turkey. Today I'm glad to present you the result of our research upon a practical technique based on laser etching to design interdigitated electrode for supercapacitors. The outline of this presentation are as follows. First, a general introduction to electrochemical energy storage systems is provide explanation about their features and limitations. Then a new practical technique based on laser etching is presented and showing the component materials combination, and then continue with their electrochemical analysis. Many technologies and applications require energy storage systems that can store and release large amounts of energy and provide stable power source. Electrochemical energy storage systems are able to fulfill the demands for energy and supply. They classified as a battery and supercapacitors. Batteries are able to deliver high energy density while their power density is very low. Actually, moving a charge in the structure of electrode materials leads to slower charging and discharging, and this resulting in reduced power density. Because of these limitations, we cannot use batteries for applications that require high power density. On the other hand, supercapacitors have mostly physical interaction that provide high power density. Because supercapacitors are based on electrostatic charge separation, they have much faster charging and discharging cycle. They have higher surface area, thinner dielectric that make the device with high capacitance. These are important advantages of supercapacitors compared to other energy storage devices and make them suitable for wide range of application. The conventional architecture of supercapacitor is sandwich type because it has a simple structure and easy to fabrication. In sandwich type supercapacitors, solid-state electrolytes sandwiched between two electrodes. Sandwich type supercapacitors facing problems like ion transport resistance that needs to large thickness of an electrolyte. In addition, increasing ion transport resistance causes it to decrease in power density. To overcome these problems, supercapacitors with in-plane interdigitated configuration have been fabricated. The most obvious merit of this in-plane interdigitated architecture is its featuring narrow gaps between electrically isolated interdigitated electrodes, which leads to no more needs for the separator that's used in traditional sandwich type supercapacitors. Especially by further reducing the distances between the electrode finger, ion transport resistance can be decreased, which helps to improve the frequency response characteristic and power density. In these interdigitated supercapacitors, the interspace between electrodes can be optimized to obtain high capacitance. Also, in interdigitated electrodes, the electrodes fingers are electrically isolated from each other, and this decreasing the risk of short circuit. Interdigitated supercapacitor fabricated by using methods like laser etching, lithography, inkjet printing, and beam lithography. And in this project, we use laser etching method to fabricate interdigitated supercapacitors. To manufacture supercapacitors, we start with preparation electrode materials. Here, electrode materials that were used is PEDOT PSS and graphite and DEMSO. PEDOT PSS is an important electrode material because of its good film forming ability by various fabrication techniques. High electrical conductivity, high physical and chemical stability in air are other features of PEDOT PSS. Here, DEMSO used to increase conductivity of PEDOT PSS, and graphite is an important material that their conductivity make it useful in different type of electrodes. Here, DEMSO was added to PEDOT PSS at the ratio of 20 to 1 watt per cent and stirred at the room temperature for 10 minutes. After stirring, the graphite powder was added to a solution at the ratio of 10 to 1 watt per cent, and then mixture was sonicated for 10 minutes at room temperature. Our substrate is a glasses that silver paste was drawn on it as a current collector. So the resulting solution was poured on the glasses with drop casting method. After solution was spread on the glasses substrate, the sample was dried at the oven at 70 degrees Celsius for 50 minutes. And the pattern were drawn on the coated glasses sample by using laser etching method. As mentioned before, interdigited pattern can be constructed using different methods, but here our patterning setup is laser etching. In this image, we can see the patterning setup that consists of CNC machines and laser devices that has a 5.5 watt power at 450 nanometer wavelength. The etching procedure was start with the creation of G-code of desired pattern, which was then transferred to CNC machine that have a laser head with the GRBL laser program. The G-code were obtained by using Inkscape software. Inkscape software was used to design and creation of patterns and convert them to G-code. Three parameters, power, speed, z-axis, were optimized throughout fabrication process. Powers refer to power of laser beam, speed demonstrate the laser nozzle rate of movement along x and y direction. And z-axis used to adjust the focal point of laser in the sample. That's are important parameters that must adjust before a patterning process because each of them influence the patterning procedure. After G-code of pattern was obtained and position of laser nozzle was adjusted, etching was start by executing the command given by program. The pedal PSS graphite film was etched with laser devices that control it with CNC machine without use of any resistive material and mask. Various kind of patterns were produced by using laser etching techniques. These techniques was applied to many other kind of carbon-based films with different dimension and spacing. After I adjust all of the various experimental parameters, as I mentioned before, interdigitated supercapacitors were designed and fabricated on the film. The first electrode was created as an interdigitated pattern. Overall dimension of first electrodes were 30 mm by 30 mm, comprising an interdigitated pattern with weight 1.3 mm and length 10 mm. Architecture and design of electrodes are important factors that influence performance of electrode. That's we try to design different patterns and compare them with each other. Here we start with a pretty complex pattern that was designed and etched on the glass substrate. The reason to design this pattern is to increase ability of electrodes to trap more charge and also have a higher specific capacitance. That's their name are triangular and rectangular shaped patterns. All of the patterns were designed in Escape software and sent to laser devices with GRBL laser software to perform the etching process. The overall dimension of electrodes that were designed is 35 mm by 10 mm, including interdigitated pattern with weight 3 mm and length 35 mm. Our setup are able to design an etching electrode with different weight and length, and also it can optimize gaps between electrodes. Electrodes with different spacing can be designed and etching with laser devices. We can see in the pictures the interdigitated electrodes with different spacing between their anode and cathodes. The spacing was adjusted by repeating G-codes with 0.05 mm shift in their way. As mentioned before, the laser power and the speed are parameters that must optimize depending on the electrodes and their applications. The parameters are dependent on the coating thicknesses and substrate type of electrodes. In this study, glass substrates were used, which were coated with electrode materials. We can see the pictures of electrodes that were patterned with various laser powers. The power level used in this study were set to 100, 200, 300, 400, and 600 milliwatt. It can be noticed from the image that at low power, the finger lines are not entirely ablated and the electrically isolated electrodes cannot construct. However, at higher power levels, actually more than 300 milliwatt, finger lines were completely ablated and electrically isolated from each other. On the other hand, in higher laser powers, the weight of finger lines were increased because of increased spot size of laser beam during the laser ablation process and the lateral heat transportation to eliminate abrasion. Our experimental setup are consist of systems that we design and manufacturing with 3D printer to hold our specimen during the experiment, and electrochemical performance of electrodes were analyzed by using two electrode cyclic voltammetric in 6 molar co-solution. CV curve of electrodes with rectangular and triangular shape were shown in pictures. After analyzes the two electrode in 200 scan rate, and between 1 and -1 potential range, under the same condition, we observe that the CV curve are rectangular in shape, which means it show electric double layer, a characteristic of supercapacitor. The area of triangular electrode was bigger than rectangular patterned electrodes. That means it store more charge, and it have a high specific capacitance rather than other. Other curves, charge and discharge curves, where the shape of charging and discharging curves was not triangular in shape, which may be because of internal resistance. And charging discharge time and IR drop of electrodes that have triangular shape is lower than other. Consequently, this study presents designing and fabrication of interdigitated electrodes based on pedal PSS with different patterns. When compared to different patterns, the triangular patterned electrodes show better electrochemical performance. It was observed that the proposed technique based on the laser etching is easy to apply to any kind of electrodes. Thank you.